Hello and welcome. The purpose of today's video is to explore typical IB style problem dealing with lines and planes in space. So the nature of this problem is they simply give you the coordinates of 3 points that are floating out in space, and those 3 points form the vertices of a triangle. Every question then is going to be based off of the location of those 3 points. Now in class, several of my students were working on this, and I don't think it's much difficulty finding the length of 3 sides. It's just extending the Pythagorean theorem by a dimension and finding the cosine of an angle between 2 vectors. The only caveat here, I would say, is to make sure that you have the vectors lined up in the correct position. So AB to AC is what you're dot producting, so you have to make sure that you're using AB and AC, where here I calculated CA. If I don't pay attention to that, I'm going to get a negative ratio, which is going to correspond to an obtuse angle. So we have to, again, pay attention to direction. Anyway, the rest of it's self-explanatory. Similarly, in the second set, we had to do a cross-product calculation. That's really straightforward. It's just an algorithm after all, so the only challenge here is making sure you apply the algorithm without making mistakes with negatives, and we're all prone to that. Nonetheless, they even told us what's supposed to happen, so if we do make mistakes, we could just find them and correct them. So that was pretty easy. And showing that the area of the triangle is 1/2 square root of 314 is simply a matter of taking the magnitude of the vector cross product and dividing it by 2. It's really straightforward stuff. Not to mention, this was an IB exam question. Well, the area formula is in the it's in the formula packet, so all you had to do was to recognize that, especially since they're pointing the direction. They tell you to take the cross product and then say hence, show the area. So the hence implies that the cross product is going to be used here, but I would also point out that if all else fails, you also have the law of cosines, so the cosine rule. That would also apply because anytime you have 3 sides of a triangle, you can use the law of cosines to find the angles within. But that would be absurd in this case, given the fact that they set you up for success with the question part I. Anyway, Cartesian equation. Once again, we've done all the groundwork already. We found the equation of the normal. So here's the cross product, which means that the normal vector to the plane, that is a vector perpendicular or orthogonal to the plane, is -7, -3, -16. Now, as you can see, what I did was I actually used -7, -3, -16, and then over here on the same side, I just basically made everything positive, basically effectively multiplying both sides by -1. That takes care of the risks of mistakes with negative numbers. Now, on the left-hand side, I put in the variables x, y, z, and on the right-hand side, I put in the coordinates of a point on the plane. I chose B to be 4, 1, 1 because it's informative. Gives me the 4, 1, 1. See what I did there? I'm sorry. Anyway, does it matter that I used point B? Could I get the same result if I used points A or C? And I'm not going to answer that question, but if you have an answer and you say, hey, it doesn't matter or it does matter, also see if you can figure out why. Why does it make sense to do it one way or the other? Alright, so anyway, this then is the equation, and sorry, I should do that first. There's my equation. And then I'm going to check by taking another point on the plane, substituting it in for x, y, and z, and I should get 47 equals 47. Which, by the way, by checking my answer, I got a hint as to the answer to my question up over here. So, answer that rhetorically, and hopefully you're right. Find the vector equation of AB. Once again, all the groundwork has been done for me because I have the direction vector AB, and all I have to do is pick a OA, which is the coordinates of point A turned into a vector, heading in the direction of AB. So we just add a time parameter to the direction vector of AB, and we have the vector equation of that line. All of this leads up to the reason for this video in the first place, which was we have this setup now. They're saying that there's a point, it's on line AB, and the vector from the origin to point D happens to be perpendicular to BC, where O is the origin. So find the coordinates of D. It's a little tricky to parse out this problem, but the first thing I'm going to observe is we just found line AB. And we'll notice again that IB has a tendency to guide us towards our solutions, and so if it asks us to find the equation of line AB, then perhaps we're going to need it. Now if we think about it, they say that D is a point on AB, which means the point D will be an XYZ that is a solution to this equation. Therefore, since D is a point on the line, AB, D's coordinates can be given by a function of time right there. Now, the next piece of the given information was that OD is perpendicular to BC, so I can take OD as taking the coordinates of point D and writing it as a vector. I take the BC, which was a vector that I found at the beginning of the process, part A, and we're given that OD and BC are orthogonal, therefore the dot product of OD and BC should equal 0, and it's just simply a matter of plug and chug. You follow the algorithm of dot product, set it equal to 0, and find that time equals -1/2. And now that the coordinates of D were already calculated for us as a function of time, now that I know what time is, I substitute that in for t, and I get the following point. Keep in mind, by the way, that if they're asking you for coordinates, you write as the coordinates of a point. If they ask you for a vector, then you write as a vertically aligned vector. So sometimes they're interchangeable in as much as, the points -1, 2, 3 and the vector -1, 2, 3, they look like they're the same thing and they're saying the same thing, but it's technically different. So please pay attention to those details and make sure that you answer the right form. Finally, though, this is the part that most people are having the most trouble with. Show that D does not lie between A and B. Now, there's a bunch of different ways to geometrically parse this out. You can do this using distance formulas or any number of kinds of things. But once again, because it's a double I have a feeling that work I did for part single I is going to help me answer the question for double I. So here's my logic and reasoning. AB is a line. The line AB starts with the vector OA. In other words, the line AB starts at point A, and if I allow time to equal 1 unit of time, 1 second, 1 minute, whatever, that's going to take me to point B, because A is in the direction of B, and at 1 second I'm going to be at point A, and we'll move to point B. If t is equal to -1/2, then we're not going from A to B, we're going in the opposite direction from A to point D. So here's the way I frame an argument. Since AB starts at A, and when t is positive, you get in the direction of B. Since t is negative, we're going to go in the opposite direction. Therefore, D is not in between A and B. Simple argument, just like that. But of course, that argument cannot be framed unless we have a complete understanding of all the work that preceded it. So a couple lessons to learn here. Number one, IB questions that are multi-part, like this one is, have a tendency to guide you or lead you in the appropriate direction. So try to make sure before you do anything that you've utilized work that you've done prior to answer the newest problem that you're working on. And the second piece here is, just make sure you understand, because if you don't comprehend all of the steps that led up to this, then it's going to be very difficult to answer the last question. If you do comprehend all the steps that led up to this point, no pun intended, then this is an easy solution. So anyway, thanks for watching.